flyback is the most common topology for offline converters. Traditional ways to improve efficiency normally involve an active clamp flyback that recirculates the leakage energy and at the same time allows the primary switch to achieve zero voltage switching. This, however, would require additional circuitries though. For example, normally a high-set MOSFET that needs to be high voltage rated, and a controller that needs to have a level shift feature to be able to drive that clamp MOSFET. All of this would add on system cost. But now we have a new way of achieving zero voltage switching with no additional circuitry. Here I have the schematic of InnoMux-2, where zero voltage switching can be achieved with no additional circuitry. We simply just leverage the existing synchronous rectifier, the SR MOSFET here, to accomplish that feature. So we call this the SR ZVS, where we optimize for system efficiency and also allow for higher switching frequency at the same time. The overall system efficiency can be improved by as much as 1%, depending on your application. Let's have a look at some waveforms. Over here, first of all, I have the drain to source waveform of the primary switch and the gate of it. And I also have the SR gate, the current waveforms, primary current, and secondary current. So this over here is caused by the leakage inductance. When you turn off the primary switch, you'll see that voltage spike on your VDS primary. And this over here is what we call the idle ring, and it happens when your secondary discharge current becomes discontinuous. As you can see, when we don't have any zero voltage switching, even if we do have valley switching, we're still turning on the primary switch when the voltage across it is quite high. These are the waveforms you're going to see on a traditional flyback with no active clamp or zero voltage switching. To achieve zero voltage switching with SR only, here's what we need to do. During the idle ring period, and before turning on the primary switch, we need to turn on the SR gate for a very small period of time. This is because we want to create a reverse current on the secondary side, from the 5 volt to ground, through the body diode of the selection FET here, and then the SR. So the direction is like this. That reverse current is then commutated back to the primary side, also creating a reverse current on the primary side. It'll flow from the VDS primary node back to the high voltage rail, discharging the voltage across your switch. And at nearly 0 volt, if we turn on the switch, that'll give us zero voltage switching. On the waveforms, it'll look like this. So before turning on the primary switch, we need to turn on the SR for a small period of time. It'll be somewhere over here. That's going to cause a reverse current on the secondary side first, and then a reverse current on the primary side. This current will be very, very small. What's important is on the VDS primary node, the voltage will look something like this, and then start decaying until close to 0. If we turn on the switch at this point, that gives us zero voltage switching. The ZVS function is only available at DCM. This is because in order to create this reverse current, you need a secondary current to be discontinuous first. So for designers, we normally design the power supply to run at DCM at high line. This optimizes the switching loss and the component stress. And for low line, we design it to run at CCM to reduce the RMS current. So at low line, when CCM occurs, the voltage across the switch isn't too high. So not having ZVS shouldn't be a problem. You might be asking, is the SR on time over here always the same? And the answer is no. Because the amount of time that the SR gate is turned on here depends on the energy that needs to be discharged here. And that's related to many factors. For example, the input voltage, or the transformer inductance, or the straight capacitance of the switch itself, or even the loading condition. So the SR on time here, all the voltage decaying time over here, they're all adaptive, calculated and adjusted continuously to make sure that the SR ZVS is operating at its optimal condition. To learn more about InnoMux-2, visit power.com.